Welcome everybody, and thank you for the introduction. As everybody knows, I've been working quite a couple of years on something obscure. Trying to work to like a new generation of cinema where you could actually walk around in the movies, and we set the first baby steps into that direction. I would first also like to say that as a side note that I'm streaming this presentation as video. So videos that are like slides that are videos will look good, but slides that contain only text will look less good. But that's normal. Most of it are videos anyway. So also you can actually download the PhD thesis, because normally you would be handing around books now. You can download it at phd.rubenverhack.de. So I will first discuss 3D worlds and virtual worlds in general, and I will explain what the limitations are. Then I will go towards camera-captured virtual reality, so that is virtual reality based on images, and I will explain what the limitations are then, and then I will present my solution that was the core of my PhD, which is kernel-based representations of images and light fields. So first, 3D worlds. So this is probably one of the first 3D worlds that was made, where you could walk around, look around. It's a predecessor of Wolfenstein 3D. The goal was to save people. This is 30 years ago. Nowadays, you have much better quality, better graphics. The worlds have become much wider. The moves you can make have become a bit more spectacular. But all of this is only possible because you had a whole team of 3D artists that model, create, and design every piece in this world. Every bus, every building, every room, table, chair is hand-made, hand-modeled, and then material properties are also added to each object. Which is very labor intensive, all of this process, but it can generate extremely nice graphics. So in general, in 3D worlds, you have enormous freedom for the user, and it can produce extremely high visual quality. But what if I would like to have a virtual representation of a real life environment? For example, what if I want to have a model of the room where I'm sitting in now? So I took 200 photos, I think, here of my girlfriend, loaded them into a program. And this is like, and an algorithm will then look for the key points that are available in every image. It will look for correspondences of these points in the 3D space. That will try to estimate the geometry, and then also will do the approximation of like the texturing and everything. These photos were taken with my cell phone, so this is not a professional setup, but it already has a fun effect. But if you look closer, you will see many small issues and that are typically present in 3D modeling. For example, if my flat had been on fire, it would have been very hard to model fire and smoke, etc. The reason why is this also problematic is there's a psychological aspect which is called the uncanny valley. If we look at a neutral object, we have a neutral emotion to it. But the more it starts looking like a human, the more of a positive reaction we have towards it. That's why start liking animals, stuffed toys, cartoons, and so on. What we also really like looking at humans. That gives us a lot of positive emotional reaction, but something in between is really off-putting for humans because it reminds us of disease, zombies, demons, all of these things. So as a side note, this is actually why Nintendo, for example, chose to not try to completely copy or simulate or represent humans, but went more for a cartoon style because it's just a bit easier. and that you could never do it 100% right anyway. And I agree with that in some extent. This is an example of the holoportation project of Microsoft, which is a really big engineering feat in which a person can be scanned in one room with 64 cameras and then in real time be communicated towards another room, for example, be displayed. However, it still feels a little bit awkward. You could then imagine settings that have like a lot more cameras, much more structured light. And they've done these things. This is, for example, when they scanned Holocaust survivors telling their story, and like that you could then look at them from every angle while they were telling their stories. But it's just not as practical to work with. So my point that I'm trying to make here is that if you want to have like freedom in a game, maybe it's better for us to stick to photos and not try to model the 3D geometry behind a scene, because it's such an inherently difficult problem. And photos are just nicer to work with. Now, how can you do this? And this is the world of image-based virtual reality. What should we imagine in a world that is image-based? A couple of years back, you had the mannequin challenge, for example, in which that everybody had to stand still, and then one person went around with the camera. And this is a little bit the look and feel that you would need, that you would expect from a movie that you could see in VR. You could be able to kind of walk around, look at it from different angles, and so on and so on. Oh, this is obviously a bit of an extreme example, but this is kind of where we would want to go at one point. But then with moving actors, which is a whole other story. One version of image-based virtual reality that we have now, where you can walk around and look around, is actually Google Street View. This is my street. You can just kind of walk or bike in the street, look around. But the problem here is that if you look around, you will see you have this cyclist behind us, and every photo is in a different position. This is because like the images are taken at different positions each time and at different times. So you could never have a movie like this because you would need to put a 360 camera everywhere in the room or in the space that you would want to capture. I mean, that's impossible because all the cameras would be looking at each other. Luckily, there's a technology called light fields and light field rendering that give a solution to this. And this requires that you have a wall of cameras very tightly packed together. But if you have that, you can extract new viewpoints and put a virtual camera in the room. So you can put the virtual camera behind the wall or in front of the car. It can look left, it can look right. And this is only possible if the cameras are close enough to each other. Imagine here that you have this is taken with a small wall of cameras, so to say, and then a virtual camera can look at the frog from left, right, can go a bit backwards, and a bit forwards. And this is all based on images. We do not know the geometry of this frog. We do not know any of the light reflectance properties of this frog. We don't even know that we're looking at a frog. And this makes this, because of that, we sidestep a lot of the problems that exists in 3D modeling. This works as follows. I made a quick animation. So in your new virtual camera, if you want to know the color of a pixel, you put your focal plane on an object. So that object is in focus, like this car. And then you trace back that pixel where it was in the original cameras, on your wall of cameras. And all of these cameras give you now that the pixel should be red, which makes sense because the car is in focus. This is different if the car would not be in focus, like in this example. If we put the focal plane on the bushes in the back, and we do the same thing again, we expect the camera to be out of focus, so completely blurred, as if it were with a real camera. And so you would then go back and ask basically the cameras, okay, what kind of color would you expect for this pixel on this focal plane here? Two cameras would say red. Two other cameras will say green, because if you draw the line from that camera to the back to that point on the focal plane, they're green. So it will be a mixture of red and green. So it will be blurred there for that one pixel. Putting the focal plane back to the front, you then have again that if you for one pixel on your virtual camera, and you go to your focal plane, it's basically like refocusing from the background onto the curve. If you have then the intersection on that focal point, you draw again the lines back into the original cameras and look on their images for the pixels that correspond to that. So basically, you try to retrace the light rays that were present in that room. And again, here, if you would be looking at the next to the car, you would then have a pixel there. Again, because you expect here that the background is blurred, because only the car should be in focus. Two cameras see that point as red, and then two other cameras see that point in green. So this will give you again a mix between the two colors, which you would expect because the background should be blurred. And this allows you to have a really cool effect that you can change the focal plane in post-production. So after you've taken the photo with like a wall of cameras, you can change the focus afterwards. This is very important in cinema because at this moment this still happens mechanically. So you take the shots and then afterwards you can never change the focus again. But in this case, this is, for example, the cat of Glenn here in the audience. You can see that you can change the focal plane. You can actually do this with a lot more different camera setups, but I will be discussing this only with walls of cameras because it's a bit easier to understand. But for example, on the right, you have the camera setup of Google. You have an arc of cameras that spin around. In this way, you don't need as many cameras, but you can only capture a scene that is completely still. You cannot have a scene that is moving around because you don't have an image for every point in time. I, during my PhD, built also one of these walls of cameras, but in the cheapest way possible. So it's just wood that we laser cut it. We put mini computers on there, Raspberry Pis, and Raspberry Pi camera on the front. And all this is really cheap. One of these panels costs about €1,000 to make. And it can take, one such panel can take 9 photos. So this is 9 times me working late. And then you can see that it's 9 times me, but the image is just slightly shifted. Given this, you can already do a little bit of light field rendering. And here, the thing that is in focus nicely shifts from left to right. You can move a bit backwards, forward. You can change the focal plane. But the main thing that you see as well is that whatever that is out of focus has this kind of ghosting effect. You can see that it's like all different images that are overlaid. If we would have had a lot more cameras, this blurring effect would have been a lot nicer, but your camera would be more expensive to build. And this is software that we wrote during PhD too. Actually, and the goal I was working for in the end of 2019 was to make a whole wall of these panels to present on the public defense. But due to the corona circumstances, this was not possible. So I'm just showing you some photos and some photos of the cable mess that came along with it. So the idea is that to eventually go to completely big walls of cameras and so that you can have or look at a scene from different angles and walk around and then have more of a sense of presence in photorealistic quality. You could then also imagine having compositions of these camera walls in which then users could walk around in these hallways and even turn left, turn right, and so on. If we think of virtual reality, we always think of these huge head-mounted displays, but you need to think of virtual worlds as anything you can kind of navigate in. As we saw in gaming, you can navigate in a 3D world with just your mouse and keyboard, but also there's new things coming onto the market like lenticular displays. These are TVs that if you look at it from a different angle, you will see a different view, a different camera viewpoint. This is not the case on your television now, and this is not the case with the old 3D televisions. You would always see one camera angle. TVs like this give you a really sense of presence because you put your eyes see something different, and if you walk around, it's like looking at a window. It's not looking at a flat surface where everything's projected to. It's like you can see through the television. It's a really cool effect, and this is also a form of virtual worlds where you can have you can choose where you stand and that you will see something different. So basically, what is the problem at this point? We've got cameras, we've got ways of showing everything, but the problem is data. This is an example of a light throw camera that was introduced a couple of years back from light throw. It never really came to market, but you could rent it. It had like this small wall of cameras inside this big tube, but it's actually one camera, but it has like a lot of small lenses in there so that it kind of mimics having a lot of small cameras in one big camera. This allowed you to do that refocus effect that I showed, but the thing was that you needed almost a server farm to be attached to the camera because it produced about 400 gigabytes per second. 400 gigabytes per second, if I want to put that into context, I looked up my hard drive on bol.com, which cost around 115 euros. It can store 500 gigabytes, and you can write to it 2.5 gigabytes per second. But we need 400 gigabytes per second. So what can you do then? The only thing you can do then is to write in parallel. So you need 160 hard drives in parallel, and that costs then already like 18,000 euros. And the worst thing about it is that it would already be completely full in 2.3 minutes. So you can understand that this is just worthless, and it's not a surprise that it's not really on the market anymore. So now they're shifting more towards basically Google bought them, and things called it secretive, but I cannot imagine that systems like this produce less data. So to give a short recap before going into my research, is that the only thing you need to remember here is that if you have a camera of walls, you can position virtual cameras behind or in front of it and turn it around, and you can simulate some hardware effects like depth of focus. That's great, but it just involves enormous amounts of data to a very problematic extent. So we've tried to look for a solution for this, and we actually thought that like maybe we should abandon some concepts that were typically present in video coding. Video coding has a history now of about approximately 30 years. That started off with JPEG in 1990, and they have brought out newer versions of these ideas to save and store images and video, but they still use the same basic concepts since then. I was born in 1989, so this is basically as old as I am. And to show this, like I actually met the inventors of JPEG here. These three guys, I met them at a JPEG conference for the event of 25 years of JPEG, and we then captured this on a JPEG. So I'll do a rundown of the basics. I won't go into details, but there's some of the issues that you need to understand, and I'll go through it quite softly. So an image is a grid of pixels. Every pixel consists of three numbers: the amount of red, the amount of green, and the amount of blue. Just as a painter can mix colors into a new color, your computer screen displays like a whole spectrum of colors based on these three basic colors. And a new iPhone camera, for example, has 12 million pixels. Video is then a sequence of images that we call frames. And video has one very, very nice property, is that time is linear. Once you know one image, you know which one should follow on that, and then you know which one should follow on that. You only need to transmit the difference to the image you saw before. And because of that, you can save a lot of data. The problem is that this method of like predicting one image from the other becomes harder in camera captured virtual reality. There's a huge number of possible frames, and in contrast to video, you do not know which frame is needed at a point, because the viewer became the director. Before, you had the director saying like, okay, now we're looking at that person, and now we're looking at that person. But two different people can look at those two actors in a different way. So you cannot exploit that side of video. So we thought of maybe let's just abandon the most basic building block of images and get rid of pixels and replace it with a newer thing. So whereas pixels are small, you need many, and they can represent only a single color, we introduce kernels that are bigger. They represent patches of color, and they can represent color gradients. And color gradients are a transition between two colors, for example, from red to dark red. To give you a little more intuition about what we mean here is that, for example, when you have this patch of or this square of pixels, one half blue, the other hand red. If you look at this from a pixel perspective, you would say blue, 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 red, 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 blue, 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 red, 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 and so on and so on. If you look at this as a human, you identify two patches. It's a blue part and a red part, and they have a strong border. So we represent this as such using the kernels. Kernels is a bit of an abstract given, but we visualize this by using these ellipse shapes. If you would, for example, want a softer transition between those two parts, you could make these kernels overlap, and then you have a soft transition from the now blue to red, but you still need only two kernels that overlap a bit more. As I said, kernels can actually also represent a gradient by itself, a transition between two colors. So for example, this left side and this right side can each be represented by a single kernel. So this batch of 256 pixels can actually be represented by these two colors, these two kernels, sorry. And the idea is that these kernels kind of fight for dominance over when we want to show these things, we want to show pixels again on the screen. The kernels are only an internal representation, are the things you save. And I will go through an example now. slides. Yeah. Okay. So from your camera you get 32 by 32 pixels. For example, you identify where these kernels lay, and then when you want to display them again, you let them kind of fight for dominance over the area in the image, and you then let them color in that area, just like painting by the number. And then generally we want to have a small file size, we want to have fast loading, and we want high visual quality. But we only need to save the kernels, no matter how many pixels they can produce. Identifying the kernels are probably one of the hardest things in our system and how we envision it, because it's an iterative process. For example, you start here with an initial guess where you think the kernels would be, and then iteratively you refine your solution until you've converged to a solution. Then, for example, for this image, you would have a kernel representation is the thing that you save on your hard drive like this. And you need to think of this as commands that you would give to a painter, like where he should put brush strokes to paint the whole image. The more kernels you add, the more detail that you get. But the more kernels that you have, the bigger your file size becomes. Every kernel, so recap, so every kernel represents a number of pixels, is responsible for a certain area in the image or video, and it represents a color gradient. So we saw for photos, a kernel, 2D kernel represents a patch of pixels, but what about video? So you saw that the video is a sequence of images. So if we zoom in on this red square on his blue shirt, you would then see that we have 256 pixels repeating itself for 30 frames, given that he doesn't move it in that 1 second. Then we could still represent this also with only 2 kernels, but kernels that have a time dimension as well, because they represent a patch of pixel over time. A video would then look a bit like this. So you have on the bottom is the first frame that you see, on the top is the last frame that you see, and the time goes upwards. And you can see that these kernels, these cigar formed shapes, they actually illustrate patches of color and how they move over time. And I have a better example now. So you have on the left side the original, and on the right side we made a kernel representation of that video. And if you look to the background, you see that the background slowly shifts from left to right because the camera is moving the other way. If we then look at these kernels, and if we choose some and let them fight for dominance in their region, you can see that they start filling up a volume, and that they still represent the background, but they represent a patch of the background in every view, and it just moves along with the motion of the wall from left to right. So you don't need to repeat yourself, even if the view changes a bit, because it can steer along the motion. So what about light fields? Light fields are these walls of cameras, and these walls of cameras allowed us to look at the frog from different angles. It captures a set of images from the same scene, but all the images are just slightly shifted. So how does this look like in pixel terms? You will have, if you zoom in again on that red square on his blue shirt, you will on the same position in every image see that it's still a blue patch and a red patch, but only shifted. But in total, you've already spent 3,800 pixels on those 2 patches. But you could still represent this with only 2 kernels. But now it becomes a little bit more tricky to visualize. So bear with me. These kernels have 4 dimensions because you have 2 dimensions because an image is 2-dimensional. And then also you have a horizontal camera movement and vertical camera movement. So main insight is that we want to avoid repetition of pixel data if it is within the same image, or if it's in video when the patches of pixels are being repeated, or if it's in these walls of cameras where in each different camera viewpoint they get repeated as well. And we call these dimensions in which the kernel can stretch. For example, this is a light field captured of a bike. Using one of those cameras that has actually tons of tiny lenses in there, so it mimics like a tiny wall of cameras where all the views actually are super similar. They just are 1 or like 5 millimeters away in camera distance. If you then like go through all of those views from top left to right bottom, you see the movement on the left. And if you want to visualize this 4D space, this is a bit wacky, but this is just for that I need this for the next slide. Is like on the right and on the bottom, you can see how this horizontal and vertical red line, how they move when you move your head from left to right. So basically, if you look at the video on the left, you see the white background in the middle, and this moves from left to right depending on the camera angle. And this is what is being shown in these 2 images on the right and bottom. Anyway, in kernel representation, we can then now do these kernels in 4 dimensions. And this white background, in the background, you have this, we can represent this, this patch of white in the background that moves a little bit depending on how you move your head by a single white kernel. I don't know if you can see my mouse, but this part and this part, this is still the same kernel. And they can generate as many views as you want. It can generate views in between camera angles, which is actually a remarkable feature. Here on the right, you have the original. This has 40 million original pixels, and on the left, we can reconstruct basically the same views using only 9,000 kernels. That means that one kernel spans roughly 4,600 pixels. And here you can see where like where the real benefits start to come from the kernel representation. We zoom in on the tire of this bike. You can see that even though like we move the camera angle from left to right, the parts of the tire are being reconstructed by the same kernels, and we could even find views in between that. Why is that important? Like I showed you this before, where we could do basic light field rendering using only 9 cameras. But because with kernels that we can interpolate views, because we don't have this idea anymore of discrete pixels or cameras and certain points, we actually have infinite cameras in between all the real cameras that were on that panel. This allows us to do a lot better light field rendering, where you can go forward a lot more up until you get some artifacts, and go backwards a lot more things are in focus. This software and the video was made by Martin, who is being zoomed in at now, and who is also continuing the research on these kernel approaches. It also allows us to visualize how the scene was actually constructed by these patches of pixel data. So if we already have photo, video, and light fields, what will happen if we want to have a wall of cameras that record video and not just a single image? Then we have a combination of video and light fields. So then we have actually a bunch of images of the same person, slightly shifted and repeated every like 30 times per second. You would then have, if you zoom in on his image, on his shirt again, and you would have the same blue patch and red patch slightly shifted and repeated like how many times? 30 times per second. This would result already in 120,000 pixels, and this could still be represented by only 2 kernels, but now 5-dimensional, which is pretty hard to draw. But there we go. On the left side, you have the original, and on the right side, you have the reconstruction. I made this video in such a way that you can see the camera turn around a little bit, but yeah, the effect is minimal here. But one kernel spans 18,000 pixels in here, and here now I can show you a bit more. So if you look to this train a little bit more from left and right, I hope it's visual through this live stream. You can see that every view is actually generated by all the same kernels. If you go through the time dimension, you can see that, for example, in the background on the right, these kernels have a long lifespan. They span and live for a large number of frames. They don't have to repeat itself. A lot of frames are being generated by the same number of kernels. So where for photos, one kernel would cover 15 pixels more or less, and like your video, one kernel starts spanning over 15,000 pixels, which is already a lot more interesting. In general, photo and video are already solved pretty well, in my opinion. But for light field and for light field video, when you want to go to these camera captured virtual reality, then I believe that the amount of pixel data just becomes too much. And we have shown in papers that we can achieve the same quality as normal video coding tools, like state of the art, where people have worked on for hundred thousands of man hours. And we, with a couple of colleagues together, we can produce something that we have the same quality, but we require 4 times less disk space for some videos. For other videos, there are sometimes small problems, especially when there's like grass and really fine texture on clothing. But this is mainly because we just not have had any time to look at it. The last image type I could think of and during my PhD were 360 photos. And this is the last one. So 360 photos, or camera takes a photo all around, and what it does then is you kind of project that sphere onto a flat image, just like when you have the world and you want to present it on a map on a piece of paper, you need to do some projection. This has some disadvantages because it will always stretch out some regions and shrink other regions, which means that you will then end up spending a lot of pixels in some areas and not enough pixels in other areas. So the projection thing is actually something you want to avoid. We've shown that by using these kernel representations instead of pixels, that you could actually just keep on operating on this on the sphere, and that you don't have to do any projection, which solves those problems. Promise you some images and colors. So this is a 360 image with a low number of kernels, and then if you add, if you use 200 kernels, you can have a 360 image in high detail and super good quality. So to wrap up, 3D graphics are currently not practical enough for representing natural scenes. Luckily, there's something called light field rendering, which allows for freedom of movement in images, but it requires extreme amounts of pixel data. So my PhD was at the idea of let's just get rid of pixels and find something, a new core building block for any image type. we have shown that it works for images, video, light fields, and light field video, which is quite remarkable because up until this date, there is no system that you can just use for video and then also use for light fields and just for images. And this means that like if you work on this system and you improve it for one type of image content, it will be improving it for images, videos, light fields, and light field videos all at the same time. Nevertheless, we still have a really long way to go. Everything is still, these are still baby steps, but we've taken up the challenge of like trying to rethink how we would just redo all of this from the ground up. And over all these years, we've shown that like we're probably onto something. So I'm very, very curious to see where this research goes in the future, even though this is hopefully the last time I make a presentation about this. Okay. Thank you. Oh yeah. No. What? One thing maybe for the people that want, when you saw that I made that like a virtual room about this 3D scan of my apartment. This is open source software. You can use it. I've had a lot of fun using it. So that I would definitely recommend. Also, the TV was called from Looking Glass Factory, and these are some other sources. And you could download the PhD at phd.rubenverhack.be. Yeah. Okay. Now I'm done. Thank you.
Okay.